All right, so the last couple of days, okay, we've been going over work energy theorem, but we've just kind of glazed over what potential and kinetic energy are. So I just want to go into a bit more detail about what each type of energy is, what affects it, that kind of thing. And then we'll kind of finish up work energy theorem today and possibly even move into conservation of energy, which will be completely reviewed from Science 10. And we'll work on kind of conservation of energy tomorrow and Thursday. And then on Friday, probably do like a unit exam review day. Monday, I booked for us to do a lab on conservation of energy and energy conversion. And then Tuesday, we'll probably do our final thing on power. There's only like one multiple choice question on power on the whole test, so it's a pretty minor lesson. Okay, we'll do our stuff to do with that on Tuesday, and then we'll have the unit exam on Wednesday. Okay, we may finish a little bit earlier than that if conservation of energy goes really well. But I'm guessing that because online learning for you guys happened during physics last year, regardless of which semester you took Science 10 in, we're probably going to need to spend a little bit more time on conservation of energy because you're not going to be as familiar with it as students usually are. Totally not your fault, unless you were that kid who logged into Google Classroom and turned off his camera and walked away from the computer. Then it's totally your fault. I taught it. So, I don't know if that's you. I hope none of you did that. I know none of you did that. Okay. But I did have one student who did last semester because I called on him every time. Science 10. Hey, can you answer this question for me? All right. So, we're going to talk about gravitational potential energy first. Okay. Obviously, gravitational potential energy is energy due to position. Okay, as all potential energies essentially are, with the exception of chemical potential energy. Okay, so it's energy due to position. The further from the Earth's surface an object is, the more potential energy it has. Now, can potential energy do work? It cannot. Okay, that's the weird thing. It's a form of energy, and energy can do work, except potential energy can't. It has to be converted into kinetic energy before it can do anything. Moving objects do work. Objects perched above the ground, hanging stationary, don't. Okay? I'm not afraid of a big load of construction materials hanging over me. I'm only worried if said load of construction materials falls. Then it concerns me. Okay? As long as it's hanging there, it's not a concern. It doesn't have the ability to do any work. It has the potential to do work, but not the ability to do work. That is basically what a falling object can do. Anyone kind of follow the difference there? Okay? In the same way that if something has chemical potential energy, that's great. Gas doesn't release heat until it's on fire. Okay? Then it's converting that chemical energy into thermal energy. Thermal energy can do stuff. Okay? Gasoline by itself can't. Does that make sense? So potential energy has to be converted before it actually does any useful work. Right? So the main type of potential energy we're concerned with in Unit 2 is gravitational potential energy. But in Unit 4, we'll also talk about elastic potential energy, okay, which has to do with the state of an object either being stretched or compressed and having the ability or nature to store energy because of that change in shape. Right? So a spring, by its nature, can store energy when its shape is changed, either stretched or compressed. A rubber band can store energy when stretched, not compressed. It doesn't work that way. Okay, but you guys kind of follow the idea there? Okay? Some things can do that, like a bow that you would use to shoot arrows with, okay, has the ability, when I pull the ends together by drawing the string, okay, that puts potential energy into it. So again, you get potential energy by doing work. Okay? I have to exert a force through a distance to lift something. I have to exert a force through a distance to compress a spring, stretch a rubber band, pull back on a bow. Okay? All of those things involve me doing work, just that energy is going to be stored temporarily until it's converted back into useful kinetic energy. Okay? There you go with that. Okay. Now, potential energy is one of the things we use to create fear when we're talking about amusement park rides, because that little bit of, kind of safe fear that amusement park rides provide, okay, is related to the fact that we understand being high above the ground means we could fall. It's instinctual. Okay? If you don't have that instinct, you can be an adventure sports person. Okay? Because some people don't have it. They have zero fear. They jump off buildings in squirrel suits. Okay? I am not that person. Okay? I used to be like that. I could climb mountains and not be afraid. But then I had kids, and then suddenly I became aware of my own mortality. Okay? So you have to be, understanding of the fact that if there's height, there's potential. Okay? I could fall. As I fall, I'll convert my potential energy into kinetic. I'll go really fast, and that'll hurt. Okay? That's where potential energy comes in, and that's how we use it in an amusement park ride to create a sense of danger. Okay? How many of you have been to West Edmonton Mall? Okay, have you ridden the rides? Okay, not as many. Okay, we used to do a field trip to West Edmonton Mall. Okay, every semester. We don't do it anymore. But we would ride all of the rides, and we would take measurements on them and whatever. Okay, and without exception, the rides all have some point where they're higher than another point on the ride, because all kind of classic amusement park rides have the kind of, we have to put work in to give the ride the energy it needs to do the rest of the thing.
Was that like just as a class, or like?
Yeah, no, like we would take all the Physics 20 classes.
And just take a bus up
to West Ed, yeah.
Like for a day or
for a
like
day?
a night?
For a day.
Okay.
Yeah, we leave early in the morning and come back late at night.
Is there a certain reason why we can't do that?
It is no longer economically viable. They raised the ticket prices ridiculously at West Edmonton Mall. We used to get a really good deal on them, and every time we went, it was higher and higher, and finally the last time I'm like, you didn't even tell me you raised the price and it's double what I paid the last time. I'm not paying. So ended our relationship with West Edmonton Mall. Plus the cost of fuel, cost of busing, like it's gotten to the point where we kind of said $50 a head was where we were going to draw the line. And that's where we drew the line. It's just getting to be too much money for a day. All right, so with all these rides, we get them up really, really high. People get that sense of danger, and then we let them feel the danger. We let the potential energy turn into kinetic. Okay? So if you're on the space shot, which is the equivalent of this ride here, you get shot up into the air, which is really fast, and then you get to this top, and then you realize just how far above the ground you are, and then you fall back down, and you get shot back up. Okay? And you get kind of both of those feelings of incredible speed and danger, incredible height and danger. Okay? The Mind Bender, okay, which is the roller coaster, still one of the tightest roller coasters, one of the highest G roller coasters in the world. Okay? Because it's indoors, and by its nature, it has to have really tight turns. And the tighter the turns, the greater the G-force you experience. Okay? But it also starts off like most roller coasters do, a slow, agonizing trek up the first really big hill to give you all the potential energy. Because there's no place on the ride after that first hill where energy will be added. Okay? It'll just go down through all the loops and around all the corners and whatever else. Okay? First drop, it's the biggest. It's the one that converts the potential energy into kinetic. Okay? That making sense? Okay? It's really scary when they stop the ride right there. Because we've had that happen. They don't normally do that. They normally just let it go. But we had one time where me, Mr. Dickey, and about 5 other students were on the ride, and it got right to the point where it's about to go down the first hill, and the brakes lost. So it was like against the shoulder harness, looking at our impending doom. And we're like, okay, nobody comes on the speaker to say everything's okay, or this is what's going on. We're just hanging there, looking down. And the kid who was sitting beside me, he was pulling a full-on Harry Houdini. He was halfway out that thing. I was like, what are you gonna do, like a Mel Gibson and dislocate your shoulder? Like, there's only one way out of this thing, and it's when we get to the bottom. Right? And he was like halfway out. He would have probably gotten out because he was really skinny. Okay? And I was like, sit down, dude. Where are you going? Like, even if you get out of your seat, what are you gonna do? There's nowhere to go. Like, you'll fall and die. You're better to stay on the ride. Like, at least you got a better chance here. And eventually he kind of calmed down when I showed him there's no way to get to the stairs over there, because there's actually maintenance stairs that go all the way to the top. And that's where he was going. There was no way to get there. And then eventually the ride just started. No explanation. Quietest mind bender we've ever seen. We were too scared to scream. Okay? And you know you gotta be real scared if you're too scared to scream on a roller coaster. Okay? And then they closed the ride. That made us feel even better about the whole experience. And they ran sandbags on it to test it. Like, you realize that means we were just sandbags. Human sandbags.
Is that legal?
I didn't ride it after. We've gone, I've never ridden it again. And I used to ride it like 10 times every time we went. It's the best ride in the park. No, I don't trust it. Long story, also true. Okay, so we got potential energy being work. Okay, we get potential energy by doing work. This was the relationship I showed you the other day. Okay, we said potential energy is m times g times h, and work is force times distance. When you change something's potential energy, you're working against the force of gravity multiplied by distance. Well, that's this, the force of gravity times the vertical distance. Okay, and that's why that works. Okay. So, what kinds of things would affect your potential energy besides height? Mass. I mean, think about it. Which is scarier? A piano hanging over your head or a feather hanging over your head? There's a reason the piano is more scary. Okay? It's heavier. We just have that instinctual reaction. We understand mass matters. Okay? We understand that something big can hurt us more than something heavy, or than light, sorry. Okay? All right. So those are the things that can affect potential energy. Okay? So calculating potential energy, we already know how to do that. Just EP equals m times g times h. So for something like this, okay, the potential energy would be the mass, 500 kilograms, times 9.81 times 48 meters, okay, and that would give us our potential energy. Okay? Easy enough to calculate that. Okay, I want you guys to read this one through and then give it a try. Okay, so the toy car is on this track. The top of the track is 2.15 meters from the floor. Okay, the bottom of the track or the table is 0.950 meters high. See if you can calculate the change in gravitational potential energy of the car, okay, between the top and the bottom. Super easy because we've done stuff way harder than that already. Okay, just looking for the change in potential energy. Okay, so obviously the purpose of having you do this question was not to tax your mathematical abilities. Obviously we've done stuff way harder than this, but what I want to illustrate is kind of just an important concept here that leads to conservation of energy. Right? So obviously the change in potential energy is m times g times h final minus m times g times h initial. Okay, so for this one, that's going to be 0.025 times 9.81 times 0.950. That would be my final down here at the bottom, minus 0.025 times 9.81 times 2.15. Okay. So when I do this, obviously I get a negative number. What do I get? So I don't have to wait for the calculator. Somebody got it there? Oh, nobody actually did it? Oh, you cleared the calculator. Okay, that's all right. And 0.2943 joules, but it's negative. Three significant figures, so negative 0.294 joules. Okay, so obviously there was a change in energy in this question. Was work done in this question? Okay, so the cart went down the track to the table. What caused it to do that? Gravity. Okay. Work is a change in what? Mechanical energy. Was there a change in mechanical energy in this situation? No. There was a change in potential energy. There was also an equal change in kinetic energy. In other words, the potential energy changed by negative 0.294 joules. What was the change in kinetic energy? Positive 0.294 joules. As that cart went down the ramp, its potential energy was converted into kinetic. Okay? No work was done here because apparently there was no friction in this situation. They never mentioned it in the question. Okay? So we have to assume this was a frictionless track. And as a result, no energy, no mechanical energy change happened. Potential energy changed, kinetic energy changed, but the total mechanical energy remained the same, okay? Which is what leads us to that, okay? That hopefully you learned last year a little bit, at least when you vaguely remember it, from Science 10. When our initial energy and our final mechanical energy are equal, then no work has been done. Because work is the difference between those two. If there's no difference, there's no work. Okay? And in this situation, all the cart did was convert its potential into kinetic. The total mechanical did not change. Thus, there was no work. Okay? You know, all right with that idea? Okay, so that's what I was saying. Like I didn't ask you to do this calculation to tax you mathematically. I did it to illustrate that potential energy can change and kinetic energy can change. If they change together, like into each other, then there's no work.
So how does this fit into a work equals force times distance perspective?
In the way that tells you no work was done.
Yes.
Yeah. So from a force times distance perspective, okay, the only force acting was gravity. Okay, and even though there's people that'll call that work, okay, because the force of gravity accelerates the object, but technically it isn't work because the mechanical energy didn't change. So people say work done by gravity, which is a bit of a misnomer. Okay, gravity's not doing any work unless it's actually changing the mechanical energy of an object, which it doesn't do. Okay? It doesn't change the mechanical energy of an object because potential can only convert into kinetic. The only thing that can do work in that situation is drag. And that turns the energy into something else, into other forms of energy. Does that sort of make sense?
Makes more sense.
Makes more sense? Okay. So from a force times distance perspective, yeah, if I went m times g times h, I get this number. That's the force times distance part of it. The problem is that while this number is negative, the change in the other type of energy in the same system is the opposite. Thus, they add up to 0 and there's no change in energy. Okay. No, I don't think we need to do any of this. Okay, kinetic energy. So something has kinetic energy if it's doing what? Moving. Got to be moving to have kinetic energy. If you don't have kinetic energy, if you're not moving, you can't have it. Okay, and that's because the formula is 1/2 times the mass times the speed squared. Now I already did my rant on the exponential relationship between speed and stopping distance, so we're already well aware of the exponential relationship speed has with kinetic energy. Okay, the faster you're going, you have exponentially more kinetic energy. What else affects your kinetic energy? Mass. Yeah. Okay, I mean, if you've got a little kid on a tricycle riding towards you at 30 kilometers an hour, which is really fast for a kid on a tricycle, and a dump truck driving towards you at 30 kilometers an hour, okay, the dump truck's got way more energy. They've got the same speed, but that's just got way more mass. Okay, something with less mass can't do as much work because it doesn't have as much energy. Okay, now that's a linear relationship. Okay, mass is a linear relationship, not exponential. Right, so if I have two objects and one's twice the mass of the other, okay, it has twice as much energy, or provided they're going at the same speed. Everybody all right with that? Okay, give that one a try. Super easy question. Just using the kinetic energy formula. Okay, just using this. Okay, you actually did this manipulation as part of one of those long questions yesterday, like the Indiana Jones question. Okay, so doing it this way with only this formula shouldn't give you any trouble. All right, so girl pedals like no, we don't want to do that. Okay, these two I want you to do because they're kind of what we've been talking about. Okay, so in the first one, we've got two cannons. And this is just going to show you the relationship between mass and speed, okay, and why they both have an effect. Okay, so you got one cannon that fires a 1.5 kilogram ball with a muzzle velocity of 550 meters per second, while cannon B fires cannonballs that are 1/3 the mass, but twice the muzzle velocity. Okay, which of these cannons would be more effective at damaging a fortification and why? Okay, so give you a little bit of time on that one. And then you can do the one about meteor crater. Because when things go really fast, they can make those. Big holes in the earth. You know, that whole dinosaur is getting wiped out. Okay, so for question number 2, the question is not actually asking you to prove this mathematically. It's just asking you to explain it. Now, I would assume probably most of you proved it mathematically. You punched in the numbers, okay, and did all of that math, okay? But here's all you would have to do to answer this question if it was on a test, okay? There's an exponential relationship between speed and kinetic energy. If I reduce the mass by 1/3, I reduce the energy by a factor of 3. But if I double the velocity, I increase the energy by a factor of 4. Okay? So it's still more energy than the first situation. Okay? I may reduce the mass, but that only has a linear effect. Okay? When I double the velocity, it has an exponential effect. I'm not saying it's a lot different, but it's a bit better in the second situation to lob that smaller projectile at a higher speed can do more damage. Okay, because back in the day, old cannonballs were not necessarily explosive. They were just big, heavy lumps of lead that you shot at fortification walls to make them collapse. Okay, that sort of makes sense? All right, for number 3, so we're talking about this crater here. Okay, so meteor crater is in Arizona. Okay, and it's estimated that the meteor that created it was about 40 meters in radius, okay, and had a mass of approximately 2.6 times 10 to the 8 kilograms. So it would have fit pretty neatly inside of the running track. Okay, and been, you know, about again that tall. Okay, so about another 40 meters tall. It hit the Earth at 7.2 times 10 to the 4 kilometers per hour. What do I need to do to that number? Right, divide it by 3.6 to get it to meters per second. Okay. Once you've got it in meters per second, you can calculate its kinetic energy, and then you can do part B, which is figuring out its explosive yield. Okay, which is always measured in tons of TNT. All right, give you a few minutes on that one. All right, so the first part's pretty straightforward. We just have to do an EK equals 1/2 mv squared, but obviously we have to convert the 72,000 kilometers per hour to meters per second. Okay, so we got 20,000 meters per second. Okay, and then we're going to go 0.5 times our mass, which was 2.6 times 10 to the 8. Times our speed squared, so Okay, so we got 5.2 times 10 to the 16 joules. Is that a lot? That's, I mean, it made that hole in the earth. And it's not a small hole either. Okay? I can't remember how big Meteor Crater is, but I feel like it's several kilometers across. Like it's big. Okay? It's not a small hole. Okay? All right, so now they're saying when 1 ton of TNT explodes, it releases 4.6 times 10 to the 9 joules worth of energy. Measure the impact energy in tons of TNT, because that's, unfortunately, how we measure explosive yield. We don't measure it in joules. We say it's the equivalent of this many tons of dynamite.
Isn't that like an extremely relative measurement?
It is an extremely relative measurement, but people who design weapons find it to be very useful because it gives them some sort of comparison. Okay, if I blew up 1,000 tons, or if I blew up 1 ton of dynamite, this is how much energy it would release. If I blow this thing up, it'll be so much bigger than that. Okay, like if you play Minecraft, and you got those like TNT boxes. I don't know, my kids do this all the time because I don't play Minecraft. And they're like, look at all this TNT. I'm like, okay, great. It looks like a box. Probably a big explosion. I don't know. Okay, so if we take this number and divide it by the yield of 1 ton of TNT, 4.6 times 10 to the 9, that's 1.1 times 10 to the 7 tons of TNT. Okay, so that is, so what do we got here? This is 1, 2, so we're looking at 11 million tons. That's 11 megatons of TNT. To give you perspective, the atomic bombs that were dropped on Hiroshima and Nagasaki at the end of World War II were 1 kiloton each. They had the explosive yield of 1,000 tons of TNT. This is 11 million tons of TNT. Okay? Now, scary thing, most of our modern nuclear weapons, their yields are measured in megatons. Right? So 1 nuclear warhead would have the approximate yield of about 1/5 of that, probably, which is enough to dig a big old hole in the ground. Okay. Now, the other thing about nuclear weapons is they don't detonate when they hit the ground. They detonate above the ground. It spreads out their destruction more. Okay? They do less work on the earth and more work on the things on its surface, unfortunately. Okay? So yeah, it's a lot of energy. It can do a lot of work, and most of it comes in the form of heat and the shock wave. So if you've ever seen any like sci-fi movies where nuclear weapon blows up and you always see like trees waving back and forth and buildings just getting blown apart, it's yeah, it's pretty realistic. The film they have of all the nuclear tests looks exactly the same. Okay, trees just go like this back and forth. Okay, buildings just they're gone. Okay, it's a lot of heat and it's a big shock wave. So what happens first is the heat comes out. Okay, it gets really, really hot. Things are basically just incinerated, and then the shock wave follows because the shock wave travels slower. Okay, so whatever's left is just scattered like ash. Yeah. And I thought you can rock yourself to sleep tonight with. All right. Okay, so I've got a few questions from the digital workbook that I want you guys to try. It'll be kind of our last stuff on energy and work, and then tomorrow we're going to move into conservation of energy. So I would like you guys, this is on page 5 going on to page 6 of the dynamics one. Okay, so let's say start on 1, move toward 8. And there's a few there that I'm going to want to talk about. If you get to 8, you can go on to the ones after that, including these inclined plane ones that are on the next sheet. There's a couple ones here that are mathematically very easy, but we'll need to talk about in terms of the context. But I kind of want to let you get there and try and work it out for yourself before I lay it out for you. So first off, are there any that you want me to go through before I choose the ones I want to go through?
I just have a question about 7.
Okay.
So it's 0 because at constant velocity Fn equals 0, so then,
F net equals 0, yes.
yeah, that's what I mean, and then, so then, like, 9 times 0 is 0, that's the work.
Yep.
That's okay.
Yeah, because you're not changing the energy any, like I'm pulling it horizontally, but I'm not changing its speed, I'm not changing its height, I'm not changing its mechanical energy at all. I'm working against friction, but I'm not doing any work on that box. That's why this part of the question, on the box, is the most important part of the question. You are doing work, just not on the box. The box's energy doesn't change. The surroundings energy does change. You're adding heat and sound and whatever else to it by dragging this box. Okay? Unless it's on frictionless surface, and then you don't even need to pull it. Right? Once it's moving, it'll just go on its own. So it wouldn't require any work either. Does that make sense? Okay, so same idea. 7 was one of the ones I wanted to go over. Same idea with number 3. Okay? How much work am I doing right now? None. I'm not increasing the mechanical energy of this stapler by holding it here. It doesn't matter how long I hold it here. I'm not doing any work on the stapler. Okay, I'm doing work against some other things, but not, the stapler's energy isn't changing, okay? So I'm not doing any work on the stapler in that case. So that's where the zeros come in, okay? Just so that we understand kind of why we're getting that answer. All right, so there's a couple other ones here in the energy worksheet I wouldn't mind you doing that have to do with the inclined planes. I'll make it a little bigger so you can see them a bit better. Okay, but I'd like you guys to do, let's say 3, 4, and 5. Okay, just give those ones a try. We'll see how we do there, and then we might just start talking about conservation of energy if those don't give you any trouble. Okay, let's see what we remember from Science 10. Okay. This is a roller coaster. This is a scary drop. It's like the mind bender. First drop's really scary. Okay. At the top of the hill, our cart, which has a mass of 500 kilograms, okay, is, let's say, 45 meters above ground level. And it is moving at 1.5 meters per second. I want you to calculate the speed of the roller coaster here when it is 8.0 meters. So we have 2 significant digits and not 1. Okay, above the ground. So we're looking for this. There is no friction. This is a frictionless roller coaster. It's going to be really fast. Okay? You wouldn't believe how much friction there is in a real roller coaster. Okay? This roller coaster would be crazy scary. All right, give me a few minutes, see if you can figure out VF. Okay? There's no friction. I'll also tell you, no work is being done. Okay, so the key points to this question were no work is being done, this roller coaster is frictionless. If that's the case, no energy is lost between the initial position and the final position of the roller coaster. In other words, this is a law of conservation of energy question. Okay? Energy is conserved, there is no work or no change in the mechanical energy of the roller coaster. So, the mechanical energy initial of the roller coaster will be its initial potential plus its initial kinetic, and that will equal its final potential plus its final kinetic. Oh. Okay, everybody with me so far? All right, so it's like, it looks kind of like a work energy theorem question, except instead of there being a difference between initial and final, they're equal. Okay, so we can expand that out even further to look like this. But before we expand it out, I'm looking for VF, which is part of which one of these terms? energy kinetic final, so EKF. So I want to isolate EKF before I expand any further, right? How do I get EKF by itself? What do I do with EPF? Subtract over the other side. Okay, so I'm going to have EP initial plus EK initial minus EP final equals EK final. Now I can expand it out even more. M times G times H initial plus 1/2 MV initial squared minus minus MGH final equals 1/2 MV final squared. Okay, at this point you have a choice. What's in every term? What can I do with something that's in every term? I can cancel it. You can leave it in there if you want, but in this situation, you don't need it. You're not being asked to calculate EKF. You're being asked to calculate part of it. And because there's no friction, gravity affects all things equally, regardless of their mass. So mass can cancel, right? But I gave you mass anyway, because I didn't want people to freak out because it didn't have it. But you actually don't need it.
So you mentioned earlier in another question that we couldn't cancel things because they were being added and subtracted with each other. Why does that not apply here?
It doesn't apply here because I'm not going to be bringing different energy types in, right? Because these are equal and there's no difference between the two, okay? In the other question, let me say that sounds unfair the way I said that. It wasn't in every term in the other one. Force times distance was in the other one. That term did not have mass in it, therefore it could not cancel.
So even if addition and subtraction is involved, if it's in every single term, it can be canceled.
Yeah, because every term is affected by equal. Sorry, go ahead.
You're just dividing by mass on each side.
I mean, you can plug it in, you get the same answer I get, right? So mathematically, you can cancel it. Not that you don't have to. I'll always give you the mass, just because I don't want to play that mean joke I played on people. Or I didn't give the mass in a question, and then one person came up to my desk and was like, Mr. Coder, I think you forgot to put the mass in here. I'm like, oh, it's 1,000 kilograms. And I went back to the desk, and another person came up, Mr. Coder, what's the mass in this one? 2 kilograms. I went back to the desk, and another person came up, and people were starting to chuckle because they realized, and other people looked terrified because they're like, oh my God, what is he doing? Okay, so I just felt like that was really, at that point I was like, okay, I gotta tell you mass doesn't matter in that question, but I'll just say to everybody it's the same number, because I didn't realize how much it was gonna freak people out.
So it doesn't matter that some of them are cut in half?
Nope, doesn't make any difference, because the half's gonna come over. I'm still gonna divide by the half. That factor will stay there. Just the mass, because that factor affects every one of these terms the same, doesn't matter. Okay? Gravity affects mass all the same. Okay? And that was the other part of it too, is it wasn't just gravity in those work energy theorem questions. It was friction, and mass affects friction differently, right? So there was all those different things in there. So when we do this, we're going to just divide both sides by 1/2 and then square root. That'll leave us with VF, and then we just have to plug in our numbers and solve. Okay, so we'll go through some more of those tomorrow, and we'll be doing a lab on conservation of energy and conversion of energy on Monday, where once again, we will run carts down a ramp, because, well, that's just the best way to do so many things. Okay? This time it'll work better than the friction lab, which actually worked just fine if I had realized it.
Yeah, I honestly.